I'm Ömer Tırınk and I will present my Physics 212 project, which is about quantum tunneling composites. First, I want to explain what a classical composite is. A classical composite has atoms spread so that the conductivity is uh, almost zero when there is no pressure applied because the atoms are so far apart in the composite. And once the pressure is applied, there is a power law relationship between resistance and the pressure until the percolation threshold is reached. And after the percolation threshold, the conductivity is high, the resistance is low, and it acts like a conductor. In our experiment, we use a zinc silicon composite, which shows a linear relationship between the resistance and pressure applied. And for the quantum tunneling composites, it's similar. When there is no pressure applied, the atoms are so far apart that the conductivity is zero. But the difference is that the resistance drops exponentially with applied pressure. This is because of the spiky nature of the nickel powder we use. The atoms have spikes which allow the electrons to tunnel through them, which makes the conductivity very high with relatively low applied pressure. To manufacture it, the composites we mix clear silicone and mineral spirits as a tinning agent in a beaker, and then we add the nickel 255 uh, to the silicone, and then we stir slowly for 15 minutes, and then we pour this mixture into plastic molds, and then we repeat this process for 3 to 1 and 4 to 1 mass ratios, and then we cure these mixtures until the silicone hardens in a fume hood. Here's a photo of the manufactured quantum tunneling composites. And for obtaining the relationship between the resistance and the pressure, we use a multimeter, crocodile cables, and two metal plates, a bench clamp, and a weighing scale. We squeeze the composite between the metal plates and connect the plates to the multimeter using crocodile cables. And then we squeeze the weighing scale and the composites between the bench clamp tips, and then we increase the pressure using the bench clamp and record the multimeter resistance values and the weighing scale weight values. Here's a photo of our experimental setup, and for the results, here is our classical composites resistance pressure plot. As you can see, as the pressure is applied, there is a linear relationship between the resistance and the pressure, and after the percolation threshold, which is about 55,000 pascals, the resistance is relatively low with around a few ohms. Here is the similar results for our 4 to 1 mass ratio classical composites. The result is linear as we expected. And for our quantum tunneling composites, as you can see, the resistance is very high with no pressure applied. But once we start applying it, it drops very fast until the resistance is about a few ohms. And here's the result for 3 to 1 mass ratio quantum tunneling composite. Again, a exponential relationship. And here it is similarly for the 4 to 1 mass ratio quantum tunneling composite. In conclusion, we managed to successfully manufacture a quantum tunneling composite using nickel T255 and clear silicone, and we managed to successfully demonstrate the quantum tunneling phenomenon by showing the exponential drop in resistance. And here's a video of our data acquisition.